Hello everyone, I am Jose Sundar. I am from Madras College from the Department of Physics. I am going to talk about the topic the Great Orthogonality theorem from the chapter Group Theory. As an application of the above two lemmas, which are shows lemma 1 and 2, let us construct a matrix M given by M equal to summation A belongs to G, gamma I A, X, gamma J, A inverse 1. So this is our equation 1, where gamma I and gamma J are two inequivalent irreducible representations of dimensions Li and Lj respectively of group G of order G, and X is an arbitrary matrix of order Li into Lj independent of the group elements. So let us multiply both sides of equation 1 from left by gamma IB, where B belongs to G. We get gamma IBM equal to gamma IB summation A belongs to G, gamma IA X, gamma J into A inverse 1, which gives equal to summation A belongs to G, gamma IBA. Here we are taking gamma I as a common, X gamma J into A inverse 1, which gives equal to summation C belongs to G, gamma I. Here BA becomes C, X gamma J C inverse 1B, where BA equal to C, which gives equal to summation C belongs to G, gamma I C, X gamma J C inverse 1, gamma J B equal to M gamma J B for all B belongs to G. Therefore, by the second lemma show, we have that M equal to 0. Taking the K, S element of equation 1, we obtain that summation A belongs to G, summation P, Q, gamma K P I A X P Q, gamma J A inverse 1, which is our equation 3. For our purpose, we now conveniently choose the arbitrary matrix X. For our purpose, we now conveniently choose the arbitrary matrix X to be a matrix of all whose elements are 0 except the M and M element, which we take to be unity. X P Q equal to del P M del Qn. Then we have from the above equation summation A belongs to G, gamma K M I A, gamma N S J into A inverse 1 equal to 0, or summation A belongs to G, gamma K M I into A, gamma S N per J star into A equal to 0 for 1 lesser than or equal to K, comma M lesser than or equal to H, L lesser than or equal to N, comma S lesser than or equal to Lj. So this is 4a. Put in words, this implies that the product of the Km element of the irreducible representation gamma I with the complex conjugate of the Sn element of the irreducible representation gamma J summed over the group elements equals 0. Next, we construct a matrix N by replacing gamma J in equation 1 by gamma I, that is N equal to summation A belongs to G, gamma I A X gamma J A inverse 1. So this is our equation 5. By treatment that led to equation 2, we can show that gamma I A N equal to N gamma I A for all A belongs to G. Therefore, by Shaw's lemma 1, we see that N must be a constant matrix, say N equal to A E, where E is the unit matrix of order Li. Again, taking the K as the element of equation 5, we get summation A belongs to G, summation P, Q, gamma K P I A X P Q, gamma Q power I into A inverse 1 gives A del Kj, which is our equation 6. As before, if we take X P Q equal to del Pm del Qn, then summation A belongs to G, gamma Km power I into A, gamma Ns power J into A inverse 1 equal to A del Kx, which is our equation 7. To draw any conclusion from equation 7, we must first find the scalar A. For this purpose, we take the traces of the matrices on both sides of equation 5, giving trace N equal to A Li equal to summation Ki summation A belongs to G, summation P, Q, gamma Kp I A X P Q, gamma Qki into A inverse 1, which gives summation P, Q X P Q, summation A belongs to G, summation K, gamma Qk per I A into A inverse 1, gamma Kp per I into A, which gives summation P, Q X P Q, summation A belongs to G, gamma qp by I into E. which gives equal to G summation P comma Q x P Q del P Q equal to G trace X. A equal to G trace X by Li, which is our equation 8. But due to our choice of x, trace x equal to 0 unless m equal to n, in which case trace x equal to 1. In short, trace x equal to del mn. Hence we get from equation 7 summation a belongs to G gamma km per I into a del ns per I into a inverse 1 equal to G by Li into del ks into del mn, which is our equation 4b. For L lesser than or equal to k, m, n, s lesser than or equal to Li. Now we combine the two results of equation 4a and 4b in one single equation. Summation Ia belongs to G gamma kmi into a into gamma ns per j into a inverse 1 equal to G by Li into del ij del ks into del mn, or summation a belongs to G gamma km per I into a into gamma ns per j star into a equal to G by Li into del kj into del ks into del mn. This is known as the Great Orthogonality theorem for the irreducible representations of group and occupies a central position in the theory of group representations. Thank you.